Welcome to this webinar, A Bridge to Digitalization, where we are going to have a look at charge amplifier with IO-Link technology, which we have in our portfolio since 2020. My name is Stefan Koch. I'm Product Manager in the Business Field Production Monitoring. In this webinar, we are going through a total of 7 sections. We'll spend the first 10 minutes for introduction and values, and then switch over to more technical aspects, starting with the product introduction itself. We have a look at measuring chain setup and integration, followed by a performance check in comparison with other solutions, and at last we're closing with a short recap. The product we talk about is the 5028A miniature charge amplifier with IO-Link technology, which is a smart amplifier for modern industrial applications such as robotics, packaging industry, or food and beverage industry. The smart amplifier combines analog and digital communication technology and paves the road for Industry 4.0. So we are talking about the signal converter, to be more precise, a charge amplifier that is being used together with a separate piezoelectric sensor of any type to acquire a specific measurement of a process. The product is being applied in the field level, usually close to the sensor, and then connects via extra components to the machine control system, or to a personal computer, or via other connections, possibly also to a cloud service. These extra components will vary depending on how you are going to connect the measuring chain to your system. In the field level, you may also already find other mature products from Kistler, such as the very fast 5074B digital charge amplifier with industrial Ethernet, or the 5073A analog amplifier. Both of them are also available as multi-channel devices. Let's have a quick look at currently existing applications and what customers are doing with the amplifier today, just to give you some ideas on where you might apply this type of measuring equipment. One of the main application fields where the amplifier is currently used is the installation on robotic tool heads, where space and weight are very limited. There is a lot of movement resulting in twist and bend on the cabling. We see a picture of a major application, robotic spot welding in the automotive industry, where customers have different measurement strategies or even control strategies for the process to ensure the correct joining of the car body metal sheets. It is a harsh environment with sparks, particles, and also high currents next to the amplifier. Weld currents for aluminum welding are usually in the range of 70 kiloamperes, so this is definitely a challenging environment. Digitalization directly on the weld gun makes installations easier and more robust, also in case of tool changes. Other applications for the product on the robotic tool head would be for grippers, clinching guns, die bonders, etc. The amplifier is also often used for general assembly lines, such as for white goods, food, or medical production. Typically, there is a very broad range of requirements, and high-performance applications are usually solved with our higher-level products. But many PLC-based systems work in cycle times of 1 millisecond or slower, which is also due to the large number of process sensors and actuators which are using up the available bandwidth. Together with common in-process sensors such as switches, presence detection, distance sensors, etc., the measurement of force of parts assembly or cutting processes on packaging, monitoring of torque levels on bottle cap closure, or the verification of pressure in gas or liquids is becoming more and more important to optimize process control and to document the process. So as seen in this chapter, the 5028A is a small and simple solution for sensor integration, besides existing digital type 5074B and the analog type 5073A. It targets various applications such as robotics, medical, food and beverage, but also other generic or specific system solutions in automotive or semiconductor industry. Let's now have a look at some added values you get from the 5020 A. As the device includes I/O link, we do have several benefits raising from the interface itself. The amplifier is adjustable, so you can access the parameters by yourself or by a superior system for service at all time. It provides also additional data, so you see the status of the device, and you can also access secondary process data like temperature or switching conditions. It is simple. The sensor can be directly identified as soon as it is connected, and it also implements some manipulation protections, so you can verify the device parameters as soon as this is accessible from the PLC system, for example. It is independent. I/O link is available all over the world, and almost any industrial system today ensures the integration of I/O link by its own I/O link masters. So it is also very universal. There is a wide range of standard accessories such as wireless connectors or bridges, and additional equipment for setup offline or inline. You can make use of them. Some of you may have already made your own personal experience with I/O link. It may be good or bad. Let's now have a quick look at some arguments for and against I/O link. I often hear these I/O link benefits are soft facts, and they do not justify the additional cost of the switching type I/O link sensors. And I agree, but especially when you're combining it with measuring sensors, so transport of measuring data, then the I/O link communication becomes a cost-efficient solution due to overall system cost. Integration of I/O links is complex as well. Yes, especially the generic profiles can be complex, but the mandatory IODD file allows a quick integration. Additionally, from Kistler, we use the smart sensor profiles for a quick success on basic integration regarding the measuring data and status data from the device. Performance of I/O link is limited. It's too slow compared to normal PLC components. Yes, it is limited. But still, many PLC systems run in cycle time slower than 1 millisecond, and this is where devices with COM3 speed will not limit the performance of the system. One of the additional values of the 5028 is that it is really small, so compared to other solutions, with the small footprint it has and the low weight, there are clear benefits when you're installing it on a robot toolhead. You can save a lot of weight, which adds up in your application then. And you can also save a lot of installation volume. So this may also allow you to use a smaller robot or kinematic system. Another benefit is the connectivity down to the field level. When you're using an analog device, your communication stops at the analog input-output modules. You can only rely on the data you get there, and you must believe that the device that is attached has a correct configuration. You must also ensure that the configuration data is stored on location where you can collect it again in case of service. But when you're using a digital system, you can connect directly down to the device. You have all-time heartbeat, you have all-time access, you can configure the device directly from the digital system which it is attached to, and you can use standard cabling instead of wiring. Using a digital component instead of an analog component can reduce your implementation and service efforts. Even though the device integration, parameterization, and coding for the digital component may be definitely higher than for the analog one, the recurring efforts for the device parameterization are much lower. You may also save time and costs in the device installation as you can focus on cabling instead of wiring, so less errors made there. And in case of a failure, you're also quicker in analyzing and service of the digitally accessible device. This means the total efforts for recurring machine installations are lower on a digital system at the end, even though the initial costs may be higher. So you can take benefit of the one-time integration. You have simplified troubleshooting, you have remote access, you have lower reproduction costs, and you have also lower lifetime costs of your installation. So we've learned that the 5028 suits your existing and future integration of minimalistic measurement solutions. It also enables remote support for your machines, and it saves money in your application due to lower lifetime costs. Kistler is providing 5 versions of the 5028, splitting the measuring range into 5 sections between 20 picocoulombs and 500,000 picocoulombs. The device features an analog output for voltage plus minus 10 volt, and it also has the IO-Link digital interface. You can configure the measuring range, filters, switch points, and so on. You also have a status indicator on the device, so you can see if it's a measure or a reset. The footprint of the device is identical to the 5038, which will be replaced by the 5028. The sensor connector is the Kistler standard KIAC 1032 UNF connector, and the system connector is a standard M12 4-pole connector as specified in the IO-Link specification. It features IP67 protection. It is an aluminium housing which is open on the bottom end. The device is potted, but as it is open, you should definitely mount it to a metallic structure to avoid EMC issues. The device allows 2 different operation modes, and it will automatically switch to one or the other. If you connect it to standard I/O components, it will boot in analog mode, so the analog output voltage will be active and the pin 4 will act as an input for measure reset setting. The device has then an analog bandwidth of 6.25 kHz with a total signal delay of less than 90 microseconds. But if you connect the device to an IO-Link master, it will boot in IO-Link mode. This means pin 4 will act as the IO-Link communication port. You will get cyclic measuring values and status, and you can also control it for measure and reset. You can always access also the configuration data via acyclic data, and the cycle time can be as quick as 0.6 milliseconds. The total device delay is then less than 0.6 milliseconds to the master. So the 5028A covers a range from 20 picocoulombs up to 500,000 picocoulombs. It has an analog output with a bandwidth of 6.25 kHz, and the IO-Link port supports COM3 speeds with down to 0.6 millisecond cycle time. Let's now have a look at measuring chain integrations of the device. To build up an appropriate measuring chain, it's important to understand the basic principle so that the relevance of sensor and amplifier selection is clear. The sensor has its mechanical limits defined by the load which can be applied to the crystal elements which are inside, but also from the load which can be applied to the mechanical structure of the sensor. And load is not only the desired direct load, but also results from mechanical construction generating errors like crosstalk, bending moments, friction, and so on. The resulting output signal is proportional to the applied load. So there we get, for example, the picocoulomb per Newton. The amplifier has its own electrical limits as well. So the internal capacitor defines the measuring range, resulting resolution, and also the bandwidth. The ground concept of the amplifier is also important for the electrical aspects, and it may cause an installation with insulation of the sensor or an insulation of the custom system input. There is also the option to have a time constant resistor together with a capacitor, which results in a defined high-pass filter. Finally, the integration of the measuring chain, including the cable, will also influence the signal bandwidth. An extreme application example with small load could be keyboard testing of mechanical keyboard switches. Here we have low amplitudes of only 60 grams of load with a specific tactile behavior, and this is an important quality checkpoint. This measuring task could be solved by using a small load sensor 9217A in combination with an amplifier 5028A521, which has a measuring range of 20 picocoulombs up to 500 picocoulombs. Here we can clearly see that the sensor is not the limiting factor. The sensor comes with a sensitivity of -105 picocoulombs per Newton and a range of 500 Newton. We can calculate and verify based on the signal we get in the application. 60 grams will correspond to 65 picocoulombs, and this is an appropriate value for this amplifier, so we are good to go. This combination of amplifier and sensors would also allow to measure 19 grams up to 476 grams. In IO-Link operation mode, we can use a standard 3-wire cable to connect the amplifier to the master. We can then set up the units to Newton, the sensitivity to -105, and the user range to 0.6 Newton. For digital systems, we could also do these conversions and scaling in the PLC system, but if you want to use it in analog mode, this setup is mandatory. Setup on a PLC system can be done relatively quick then. We will look at an example on a back-off PLC. First we scan for the device or we add it manually from the library. Then we set up the master, such as the cycle time that is desired for the application. And then we set all the parameters as we have just discussed before. We write them to the device and assign the parameters to the parameters we have in our program. Last but not least, we calculate the real value from the data we get from the device. So this means we calculate the measuring value times 10 to the power of scale to have a floating point value at the end. We can now go into run mode and have all IO-Link data now transmitted as Newton. We can also get the device status data with every cycle. The IO-Link value we get here show all the values within the physical range of the device. In this case, even though the configured range was exceeded with values higher than 0.6 Newton, we can see this in the graph. From this point on, the overload bit indicates the overload. We could also use the analog voltage output instead. In this example, the output voltage range limitation was configured to 5 volts, so the full scale input of 0.6 volts would correspond to 5 volt output. With the same curve, the signal would be clipped at 5 volt. We see this in the lower graph, even though the input, of course, would exceed this range. Same for the overload. We would not get the bit as we are using it in digital mode, but we would see the red light indication on the device as an indication of the overload which has occurred. There are also some other configuration options on the 5028 amplifier, such as low pass filter, so we could get rid of mechanical vibrations or mechanical noise on the signal. We could also apply the high pass filter in case we want to measure endlessly without having the opportunity to perform a reset cycle. We could invert the reset operate behavior. So for example, if the device is mainly in operative mode, in measurement mode, we could assign this to a low signal so that there is no continuous power draw by the control input. And we could also configure switch point logic for the IO-Link operation. So this means we could use single point, 2-point, or window mode evaluation on the device itself, which could be helpful if you have exchangeable, interchangeable modules which have different settings for the process. We have seen that the 5028 can be combined with a wide variety of sensors depending on the application purpose and installation situation. It allows acquisitions from millinewtons to kilonewtons or even more, or also in other physical quantities. And it provides features for application-specific adaptations like signal filters or predefined evaluation limits or high-pass filters. IO-Link often has to face serious and clear criticism regarding update rate and deterministic behavior. These are very important properties, but as the system capability depends on components and overall configuration, there is no general answer to all situations. In this section, we look at how the IO-Link interface of 5028 compares to analog and native EtherCAT regarding performance on cycle time and delay. Due to their mechanical design with high stiffness, piezoelectric sensors do have a wide bandwidth. With a raw sensor signal, including also some fast ripples, for example, from slipstick effect or mechanical shocks, the amplifier's internal processing at high sample rate allows to pass through most of the details of the signal to the analog output, and of course, within the limits of 6.25 kHz with the mentioned processing delay. Using IO-Link, we have a cycle rate to the IO-Link master. For PLC systems, this will be up to 1 millisecond, depending on the PLC system's capability. At the end, the PLC system only sees a fraction of what the sensor initially detected, but still this is a totally common data rate that has proven to be suitable for many of today's applications, for example in joining processes, clamping, handling, and so on. I've also shifted this acquisition cycles by half of a cycle to show what would happen if this would be acquired asynchronously, and we can see that the curve looks different. This is why it is important to use an appropriate low-pass filter in such applications. Looking at some real-world force measurements acquired on a manual toggle press, pushing onto a tiny end position bumper, we can see that IO-Link data keeps up really nice with the analog signal recorded on a fast 8 kilosample AD terminal. However, there was a short crack force drop caused by a groove. Zooming in, we can see that the IO-Link stream was not able to catch this event. It was simply too short. Now the question arises, is this something required for quality assurance, or is it irrelevant for you and negligible? So keep that in mind for your applications. Identify your required process parameters and the events you really need to detect. To do so, initial use of our high-performance laboratory equipment or at least some performant industrial amplifiers is recommended prior to downgrading to a cheaper solution. You might have recognized a time delay between the digital value and the analog value that was acquired. For machine builders, there are two major factors that are relevant for process controls: total time delay and jitter. Both are limiting factors for process control loops, but as jitter is time variance, it may also become a critical factor when it comes to process evaluation, combining several signal sources. To visualize delay and jitter of different signal paths, a mid-range PLC was used as a signal generator and oscilloscope at the same time. This concept allows to have the same conditions for multiple measurements and also to compare measuring change solutions regarding delay and jitter effects also with different PLC cycle times. The raw signal is generated using a waveform output on an EL4132 analog output terminal, which is then fed into two capacitors which are attached to each of the amplifiers. From the 5028, we are using the analog output on a very fast EL3702 analog input terminal, and we are also using IO-Link on an EL6224 IO-Link master terminal. On the other side, we have the 5074B industrial EtherCAT amplifier, which is directly transferring its values via EtherCAT to the PLC system. We are comparing signal transmission delay on 3 different cycle times. We have EtherCAT at 0.125 milliseconds on the left, 1 millisecond in the middle, and 2 milliseconds on the right. IO-Link is always set to 0.6 millisecond, which is the fastest cycle time that the 5028A is capable of. Looking at the first graph on the left, we see that right after the signal drop, the brownish curve, we have the pink signal coming in, which is the analog output signal of the 5028A, acquired with the EL3702 terminal. One cycle later, we have the signal from the 5074 coming in via EtherCAT, and approximately 1.4 milliseconds later, so later from the drop, we have the IO-Link data coming in. At 1 milliseconds, we see that the analog output value of the 5028 and the digital value from the 5074 both arrive at 1 millisecond, so the first cycle after the signal drop, but the IO-Link data still arrives 1 cycle later at 2 milliseconds. Looking at the last curve on the right, with 2 millisecond cycle time, we see that this is more than enough time for the signal to drop and to be acquired and transmitted via all of these 3 channels, so the analog signal, the EtherCAT data, and the IO-Link data all arrive in the first cycle right after the signal drop. Using the know-how from just show measurements and other data from other sources, the minimum delay and maximum delay, including jitter, can be determined for these acquisition systems. This chart shows the expected delay it can take in cycles until an event can be processed in the PLC system. Especially in case the control system does not use timestamps on data points, then only cycles are available to correlate data. The solid lines show the minimum delay for each of these measuring chains, considering signal transmission delay to pass the signal through the components. The dotted lines instead show the realistic maximum delay, including jitter, until an event may be detected and processed in the PLC system. Be aware that even with an active synchronization mechanism, the event may miss the first transmission cycle to the PLC, so its detection is then only possible after transmission with the following second cycle, and this is common for all acquisition systems. Sync shift time information helps to synchronize the data points for combined evaluation, but the transmission delay is always present, so it must be considered for fast and time-sensitive control loops. According to this, IO-Link is an option for all measurement tasks which do not require synchronization of multiple sources, and which can be processed with signal delays longer than 2 milliseconds. The analog signal, here indicated with the pinky color, still shows the best results with shortest delay and lowest jitter value. However, this directly depends on the conversion terminal used for digitalization. Common standard terminals are relatively slow and may cause much longer delay and larger jitter, as shown here, most equal to the results when using IO-Link. So what we can say is, as mentioned, IO-Link is capable until cycle times of 2 milliseconds and definitely comparable to other solutions. We have learned that 5028A can continuously provide measuring values to the PLC within less than 2.5 milliseconds. Delay is caused by each involved component but can be compensated for analysis, but jitter is a factor that may limit process speeds if combination of signal is required. Applications running faster cycles than 2 milliseconds are served best using devices with analog output or direct industrial Ethernet connection. Short recap. The Kistler miniature industrial charge amplifier with IO-Link technology is a smart amplifier for modern industrial applications such as robotics, packaging industry, or food and beverage industry. The smart amplifier combines analog and digital communication technology and paves the road for Industry 4.0. In case of questions, feel free to contact me anytime using the information shown below. We have received some questions during the presentation and will answer them right now.
Thank you so much for that great presentation. And now let's get to the Q&A. We do have some questions that have come in from the attendees, so we're going to move into answering those right now. If we don't get to your question, don't worry, we will have an answer for you following the webinar. Now for our first question. I am using 5030A2 now. Can I switch to 5028A?
5030A2 has a measuring range of 10,000 picocoulomb, so if you want to switch to 5028A, you need either version 531 with 5,000 picocoulomb or the higher version with 50,000 picocoulomb, that's 541. Now the issue is 5028A does not have I/O pins for range switching, so you have to decide for the range you want to go for. Besides that, we have already learned that the footprint is the same. Of course, the cable connection changes from 8-pin to 4-pin, and what also changes is the range switching level, so keep an eye on that. But basically, yes, you can.
Great, thanks for that. Okay, next question. Can I mount 5028A on a robot head?
It's definitely a good choice to mount 5028A on a robot head, as it is really small, and as we already discussed, it has both options, so you can digitize directly on the robot head if you have an IO-Link MOSFET there, and then route through the industrial Ethernet through the robot. You could also route through the IO-Link, of course. But otherwise, if that's not available, you can also route the analog signal through the robot. Keep in mind that in this case, you have to use shielded cables. You need also cables which are available and suitable for twist and bend and robotics applications, as otherwise you will have to exchange the cable quite often.
Thank you. Okay, next question. Are you going to implement the new floating point smart profile?
The new floating point smart sensor profile is definitely something we want to implement because we see lots of benefits coming from that. Unfortunately, it's not yet released, so it's in the pre-release phase from the IO-Link consortium, but it's already specified and the specification is available from the website iolink.com. And we definitely intend to launch our products, update also our existing products with this new profile as soon as possible.
Great, thank you. Okay, next question. Where can I get the IODD?
The IODD file is available through various channels. You can get them from our Kistler website when you go to the search and enter 5028A and search for that. You will find the product, and in the product page you'll find the IODD file as well. Otherwise, you can of course use the official IODD finder from the IO-Link consortium, which is also often implemented already in the IO-Link master software, where you can directly request the download.
Great, thanks for that. And now for our last question. Will there be other IO-Link devices from Kistler?
At Kistler, we think IO-Link is a good interface for small solutions, for small sensors with low power consumption and therefore also low thermal effects. And we are definitely looking forward to provide new products with IO-Link also in the near future. So definitely yes. If you intend to consider IO-Link for your next applications, please feel free to contact us and ask for possible solutions. So we are at the end of this webinar, and thank you very much for your attention. If you would like to learn more about measurement technology and Kistler, please visit our webinar section on our website.
And we are going to wrap things up right there. So Stefan, thank you so much for taking the time to be with us today and also taking the time to answer some questions. We'd like to also thank our audience members for being part of this webinar event. You will be receiving an email from us with a link to the on-demand version of this presentation, so you will be able to come back and watch this again or share it with your colleagues. And lastly, please take a moment to complete a survey which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we will talk with you soon.